Hi, I'm Tate,
And I'm Weining
and this is our circuit design problem.
for the active bandpass to filter out EMG signal. We were asked to design, as part of our problem statement, to build, characterize, and perform the proof of a concept experiment for a circuit capable of cleanly measuring the EMG. So basically, what we're talking about is electrical signals generated by muscle activity upon like either flexing or like doing some things like with your arm muscles. For like the background context of which is a prosthetic arm. Specifically, what we're asked to do is to be able to filter out and cleanly see the a frequency range of 20 to 1,000 hertz, which is the typical frequency range achieved for muscle activity within like a human arm. And what we had to do was amplify the signal to an extent such that we were able to achieve a 2-volt peak-to-peak voltage, such that it's visible, so that it's measurable. So basically, the way we approached this problem was we needed to filter out signals that were under 20 hertz and above 1,000, so we could cleanly see the EMG signal. Furthermore, we needed to be able to amplify the signal that we filtered out, such that it goes from the very almost inaudible and immeasurable the voltage that it is inside your arm to a cleanly visible around 2-volt signal. So to this end, we first designed a bandpass filter that will have a steep cutoff with its cutoff frequencies at 20 and 1,000 hertz, and the rest of the voltages, the noise either high and low beyond that range, filtered out. Because 20 hertz is so low, and that we were asked to filter out everything above 1,000, we decided a steeper roll-off of frequencies beyond the desirable range was what we were targeting in this experiment, and that's why we went for a second-order bandpass filter for our signals. Secondly, we were asked to find the difference in potential between 2 points on a human muscle relative to a distant ground. So what we needed to do was design 2 such bandpasses such that we could filter out signals from 2 points of a muscle movement, such we could take the difference in their potentials. So after 2 bandpass filters, we needed to amplify the difference between the 2 signals achieved at 2 points of a human muscle. Therefore, we decided to use an instrumentation amplifier that will allow us to put a gain onto a difference in voltage and measure voltage potential. So basically, what you will now see is the actual circuit diagram of how we achieve the ability to filter out all noise signals and amplify the difference in the potential between 2 points of a human body signal that has a frequency of around 20 to 1,000 hertz that's captured at an amplitude of at max 5 millivolts.
Knowing that we needed a bandpass filter that would filter out frequencies below 20 hertz and above 1,000 hertz, and knowing that we had to use a second-order filter, we started off by choosing these cutoff frequencies. For the high frequencies, we have this filter right here, and for the low frequencies, we have this filter right here. For each filter, as we stepped up, we needed to step up by the rule of 10, meaning this resistance value is a factor of 10 higher than this one, and so on. That prevents current leakage and ensures that we get a filter that does its job. We first established resistance values and then found C values using the equation FC equals 1 over 2 pi RC. After choosing values that we could actually find in the lab, values of resistance that we could find in the lab, we ended up with this high cutoff frequency and this high cutoff frequency for each high-pass filter. For the lows, we got a range of cutoff frequencies between 20 hertz and 21.5 hertz for these filters right here. In a similar situation for the second electrode input, we had a range of high cutoff frequencies and another range of low cutoff frequencies. These vary because we cannot get exact same resistance values and capacitance values in the lab. They are very close to what we desire, though. This is the amplification part of the circuit. We have 2 op amps inside a INA 126 amp. After the inputs are run through the instrumentation amp, we get a Vout measured over here. The Vout is determined by the two input voltages and the gain of the amp. The gain of the amp is equal to 5 plus 80 kiloohms over Rg, which is in the amp right here. These capacitors at the bottom and the top of the amp help ensure that we get rid of any 60 hertz noise coming through the circuit.
So next we're going to give you a quick rundown, at least theoretically, of how our circuit is going to affect the input wave in terms of filtering out the undesired frequencies as well as amplifying the overall output amplitude. So a quick rundown at first of how second order filters as well as instrumentation amps affect the input wave. Here's the V out over V in transfer functions individually for a low pass filter and a high pass filter. For a second order filter, you obviously multiply them upon each other. You achieve this result. For a second order. Now you move down to the moving down to a band pass. You multiply the effects of the two band passes together. This is the first second order and the second order low pass, second order high pass, right? And once you put that into your G of F equation, you use rule of logs. You break them up, and then this is just two separate portions. And we remember what each of these portions do. This is a first, second order low pass, second order high pass, and then you have your second order high pass going up like this, and your second order low pass going up straight at first, and then dropping down. And because they're second order, the canonical approximate slopes of 40 to negative 40, 40 to and negative 40 decline, and that is basically down here is what you achieve out of one of our band passes. Now, at the bottom here, we have the V out over V in as it's affected when you finally add the instrumentation op amp. Now, the V in plus and the V in minus are two band pass filters that end up resulting in this. Their difference is going to be amplified by a factor determined by the configuration of op amp to be 5 plus 80 kiloohms over the resistor we choose to plug into the op amp. In this case, we chose a resistance of 67 ohms for a desired gain of around 1200 volts over volts. So all of this will add up to be a constant, and that will provide a linear shift upwards for our bandpass bow plot. So what will end up resulting, at least theoretically, is that we will be able to filter out everything under FC low or FC high, at least with like a dropping slope, and everything in between we should keep at least consistently in this region at an amplification gain that's equivalent to 20 log of this amplification value, which we've determined to be around 1200, at least theoretically selected the value of our components. This is a demonstration of our EMG at work, and as you can see, Tate is flexing his muscles. You have the two sensors attached here relative to this ground node on his elbow, and our circuit measures the difference in the potential differences from both circuits relative to that ground, and our output leads to the oscilloscope, and you're going to see on the scope exactly what happens as Tate is continuously flexes. You can see it's continuous. You can see that. All right, Tate, you want to do one of the single ones? There you go. Where it's spiking shows where the EMG is measuring Tate's muscle signals spiking, and we're getting up to 1.5 to 2 volts.
We got up to 1.7 at one time.
Right here, if you can see channel 1 voltage, we're popping up to like around 1 to 2 volts. Obviously, the electrical signal of the muscles changes. It varies, as well as the frequency varies as well. But you can't tell that as he's flexing harder, the amplitude is spiking. And there's a few more spikes for you.
2 volts.
Yeah, there you go. And there you go. There's the EMG at work and the sick muscles.
Alright, we have modified our circuit a little to show a different type of output with an LED, a light emitting diode. What we've added is a non-inverting op amp that multiplies the amplitude of the output about 4 times. And you can see as Weining flexes here, the LED turns on. I think you can get that in right there. So yeah, it varies depending on the signal in his bicep. Pretty cool. After analyzing data from the scope, we realized our gain was not quite up to what we thought it was going to be from what we set our RG value to be. Because of the high gain and the low RG value, the roll-off actually started before we desired it to be at 1,000 hertz. It actually started around 500 hertz. This is just a feature of the amp that happens to have that kind of high or low pass filter effect.
Yes, the higher we raise the gain, the sooner it rolls off. And when we had designed it, that was not a spec. That was not a spec nature that we were made aware of. So our roll off started sooner than we thought. And on the low side, where our cutoff was supposed to be at 20, we basically ran into a problem that between 0 and 20 hertz, there wasn't that much of a difference in frequency to satisfy the omega being much smaller than the omega cutoff assumptions. So the roll off again, like Stacy, started rolling off before and didn't roll off as steeply. Basically because there just isn't that much of a frequency range between the cutoff and where 0 hertz was.
So our gain wasn't quite up to what we desired, and when we added an LED to our circuit, we actually had to add another non-inverting amp just to boost it a little bit to power the LED.
It was larger than it had to be, but we just wanted to give ourselves a little cushion, so we amplified the signal coming out of the INA by 3 times, just to make sure that when we did flex, it would top the 2.5 volts necessary to activate the LED.
Another thing that we could have improved in our circuit was just adding the amp before the bandpass filter. If we had done that, we would have only needed 1 bandpass filter instead of 2. That would have minimized parts and potentially minimized cost in a different situation. Also, that would have eliminated any potential problems with phase shift due to the difference in cutoff frequencies in the bandpass filters. Because we can't get we actually did find pretty precise component values in the lab. We actually spent time doing that to ensure that would not be a problem. But that could be a problem in a different situation.
And overall, our circuit did perform very well. As you can see, upon flexing, we were able to actuate the LED light. In fact, you can actually see by the intensity of the light how hard I was flexing my arm. Or like you can see, similarly, you can see on the scope that when Tate flexed, that you could even tell like amplitude differences when we actually try to actuate the circuit.
Mm-hmm.
So those are good things about our circuit. Like obviously it did its job, and from all intents and purposes it performed well. Obviously, like Tate said, like there were these things we could have done better, minimizing parts and potentially eliminating cutoff frequencies, but we did achieve completely 100% our design criteria, so that was positive.
And it was still a fairly clean circuit design. Using the INA 126 instrumentation amp was a pretty big benefit because we only had to use that one tiny amp instead of using multiple 747s.
And our circuit managed to all fit on a single breadboard from input all the way to the LED light, so that was definitely like representative how we were able to save some space.
All right, and that's it. I think we did a good job. Enjoy.
Yeah, and attached with this video lab report will be a circuit diagram with all the component values written out, as well as the experimental data values for the bow plot, just for references.